Subcommittee on Energy will come to order. Without objection, the chair is authorized to declare recesses of the subcommittee at any time. Welcome to today's hearing entitled Nuclear Energy Innovation and the National Labs. I now recognize myself for 5 minutes for an opening statement. Good morning, and I've already welcomed you to the committee hearing this morning. We appreciate you all being here. Today's hearing will focus on the Department of Energy's National Laboratories research capabilities and the working relationship with the private sector to advance nuclear energy technology, both fission and fusion. The Department of Energy owns 17 national laboratories, 16 of which are operated by contractors as federally funded research and development centers. The government-owned, contractor-operated model allows the labs flexibility to think outside of the box when tackling fundamental scientific challenges. The Department of Energy labs grew out of the Manhattan Project and today provide the critical R&D infrastructure that will enable researchers in academia and the private sector to develop the technologies of tomorrow. It's pretty clear that the challenges in nuclear science can be quite complicated, and we'll hear more about that from our expert witnesses on our panel today. That said, not being a nuclear physicist or anything of that sort, I'm going to do my best to simplify what we intend to discuss in today's hearing. We hope to get a better understanding of what the DO labs do and how their unique research machines and talented group of researchers can enable companies to develop new products. This is especially relevant for nuclear energy R&D, which requires large upfront costs, but may lead to revolutionary technology with long-term rewards. Folks, I would add that the United States has a definite national interest in maintaining our position at the forefront of nuclear technology development. Nuclear energy, as you know, is in a class of its own with the highest energy density of any fuel and yet yields zero emissions, the big goose egg. It is also highly regulated, often a centerpiece of global, especially national politics, and it's associated with the world's strongest economies. In the United States, we invented this technology and cannot forego, we must not forego the opportunity to export more efficient and safer reactor systems that will mitigate proliferation concerns while increasing global stability by providing a reliable energy source. Today, we're going to hear from the president of a charitable organization that has co-invested with the DOE lab to advance a specific nuclear fuel treatment process to convert nuclear waste into a usable fuel. We will also hear from the Oregon National Lab, which invented this fuel treatment process, as well as private companies developing fusion and advanced fission reactors. Needless to say, this is a unique panel of witnesses. I thank the witnesses for participating in today's hearing, and I look forward to their testimony. Mr. Grayson, Florida, you're recognized for 5 minutes.
Thank you, Chairman Weber, and for holding this hearing, and thank you to our witnesses for agreeing to participate this morning. For decades, the federal government has provided critical support for energy research and development. From solar to wind energy to natural gas recovery, many of the technologies allowing us to transition toward a clean energy economy and creating entire new industries would not be possible without federal support. And the same is true for nuclear energy. This morning, we will listen to you all regarding the federal role in developing the next generation of nuclear energy technologies. I'm particularly pleased that as part of this discussion, we will learn more about innovative future fusion energy concepts that have the potential to accelerate the development and deployment of commercial fusion reactors dramatically. Fusion holds the promise of providing a practically limitless supply of clean energy to the world. In a sense, we're already dependent upon it because the energy that we get from that fusion reactor called the sun in the sky is essential to the existence of life on Earth. It's proving difficult for people to replicate what the stars are able to do through sheer gravity, but based upon several developments in recent years that we'll be hearing about in part today, I'm confident that we'll get there, and I hope far sooner than people may realize. I do have my reservations about fission, another subject that we'll be discussing today, not about the physical process itself, but the applicability of that to our energy needs. I have described fission in a sense as a failed technology. There is a problem with spent fuel that doesn't seem to have a solution after many decades of consideration. We've had 3 nuclear disasters worldwide. But the answer to that may not be the German solution of simply scrapping. The answer to that may be to do further research and try to find solutions to these problems. In any event, I'm a strong supporter of fusion energy research, which is entirely different in terms of its impact and potential problems than fission. I believe that now is the time to build and operate experiments that are capable of demonstrating that man-made fusion systems can consistently produce far more energy than it takes to fuel them. I'm eager to learn about both the costs and the benefits of a wide range of new nuclear technologies, and I also look forward to hearing how nuclear energy can play an important role in developing a modern, clean energy economy. Again, I want to thank you all, our witnesses, for providing your insights today, and I look forward to hearing from the chairman and working with the chairman on nuclear energy issues moving forward. Thank you. I yield back the remainder of my time.
I thank the gentleman from Florida and now recognize the gentleman from Texas, the chairman of the full committee, Chairman Smith.
Thank you, Mr. Chairman. And today's hearing will examine opportunities for advances in nuclear fission and fusion energy technologies. We will hear from the Associate Laboratory Director at Argonne National Lab, the home of the world's first reactor to demonstrate a sustainable fission chain reaction. Argonne National Lab is responsible for foundational research and development in nuclear energy that has led to many operating reactors and reactor concepts that will be discussed today. These include the integral fast reactor and pyroprocessing. We will also hear from witnesses who represent private companies and a charitable organization, all of whom have invested in the development of advanced fission or fusion reactor designs. Nuclear energy provides reliable, zero-emission power. This technology represents one of the most promising areas for growth and innovation to increase economic prosperity and lower the cost of electricity over time. This will help keep the United States globally competitive. The Department of Energy's national laboratories provide vital opportunities for the private sector to invest in innovative energy technologies. This includes its open access user facilities, which are one-of-a-kind machines that allow researchers to investigate fundamental scientific questions. These facilities enable a wide array of researchers from academia, defense, and the private sector to develop new technologies without favoring one type of design. This represents a better approach than simply picking winners and losers through energy subsidies. DOE's labs also provide the fundamental research capabilities that lead to scientific publications or proprietary research. In this public-private partnership, private companies take on the risk for commercializing technology, while the government enables researchers to conduct specialized research that would not be possible without federal support. DOE's national labs keep America's best and brightest scientists working on groundbreaking research here in the United States instead of moving to research projects overseas. I am hopeful that today's hearing can demonstrate the importance of foundational research capabilities in the national labs that will lead to the next generation of nuclear energy technology. Inevitably, and I hope sooner rather than later, all Americans will benefit from this research. Mr. Chairman, before you go back, I just want to apologize to our witnesses. I have another subcommittee meeting of another committee that I need to go to briefly and then hope to return. So, but do look forward to reading and hearing what the witnesses have to say today.
Thank you, Mr. Chairman. Let me introduce our witnesses. Our Dr. Mark Peters, our first witness today, is the Associate Laboratory Director for Argonne National Laboratories Energy and Global Security Directorate, which includes Argonne's programs in energy research and national security. Dr. Peters has worked with the national labs for 20 years. In addition, he serves as a senior advisor to the DOE on nuclear energy technologies and nuclear waste management. Dr. Peters received his bachelor's degree in geology from Auburn University and his PhD in geophysical sciences from the University of Chicago. Welcome, Dr. Peters. Our next witness is Mr. Frank Batten, Jr., Chairman and CEO of Landmark Media Enterprises and President of the Landmark Foundation. The Landmark Foundation focuses its efforts on helping local education and human service organizations. Mr. Batten received his bachelor's degree in history from Dartmouth and his MBA from the University of Virginia. Welcome, Mr. Batten. Am I pronouncing that right? Our next witness is Mr. Nathan Gilliland, Chief Executive Officer of General Fusion. Before joining General Fusion, Mr. Gilliland served as an entrepreneur in residence with Kleiner, Perkins, Caulfield, and Byers, one of the world's largest venture capital firms. In addition, he was the president and co-founder of Harvest Power, a renewable energy company that turns organic waste into natural gas and electricity. Mr. Gilliland received his bachelor's degree in accounting from the University of California at Berkeley. Welcome, Mr. Gilliland. Our final witness today is Dr. John Varmintola, Senior Vice President of General Atomics Energy and Advanced Concepts Group. Dr. Varmintola oversees a team of nearly 475 from over 90 institutions worldwide who lead the way in international nuclear fusion and fission research and development. Before joining General Atomics, Dr. Varmintola served as Director of Research and Laboratory Management for the United States Army. In addition, he served as Science and Technology Advisor to the Chief Financial Officer of the Department of Energy. Dr. Varmintola received his bachelor's degree in physics from Polytechnic Institute of Brooklyn and his PhD in physics from MIT. Welcome, Dr. Varmintola. We're going to turn to our witnesses now, and y'all are recognized for 5 minutes. We'd ask that you keep your testimony to 5 minutes. Dr. Peters, we'll start with you.
Good morning. Thank you, Mr. Chairman. I'd like to thank Chairman Smith, Chairman Weber, Ranking Member Grayson, Congressman Lipinski, Congressman Hultgren, and the other distinguished members of the subcommittee for your invitation to testify here today on this important subject. My name is Mark Peters, and I am the Associate Laboratory Director for Energy and Global Security at Argonne National Laboratory. And, Mr. Chairman, I've prepared a detailed written testimony that I would request be submitted for the record, and I'll summarize it here.
Okay, without objection.
The history of nuclear energy development in the U.S. is one of cooperation amongst the federal government, its DOE, national labs, universities, and industry. The breakthroughs and designs achieved by the scientists and engineers of the National Laboratory Complex, and Argonne in particular, inform and drive every nuclear reactor design in the world today. The U.S. continues to be the lead source of innovation globally for the current generation of light water reactors, or LWRs, and small modular reactors, or SMRs, as well as leading in regulatory process, independence, and rigor. But a 30-year hiatus in the construction of new U.S. reactor projects has impacted domestic production capacity, investment in technology and innovation, and the domestic supply chain. The country's leadership in global nuclear energy could be further compromised as the world begins to move beyond the current generation of nuclear reactors to new designs, known as advanced or Generation 4 reactors, that can address the future challenges of nuclear energy. Other countries are forging ahead with new reactors that, when coupled with advanced fuel cycles, can address long-running challenges with nuclear waste management, make significant gains in efficient use of fuel, and operate even more safely than current generation reactors, further addressing lingering public acceptance and confidence challenges. Without a commitment to advanced reactor technology development and demonstration in the U.S., our country runs the risk of defaulting on the return of 7 decades investment in nuclear S&T and infrastructure. That lead position has allowed the U.S. to become the recognized world leader of efforts to control nuclear proliferation, ensure the security of nuclear materials, and promote safe and secure operation of nuclear power plants. If the U.S. is to ensure its rightful place at the forefront of advanced nuclear energy systems, it will require a new commitment to the type of public-private partnership that led to the creation of our current fleet of light water reactors. Our national labs and universities continue to work closely with industry to accomplish much of the research necessary to facilitate advanced reactors, but substantial work remains. A new generation of advanced reactors will require refinement and demonstration of new technologies, as well as a test reactor and test bed for demonstration of advanced reactors. More work remains to be done on advanced fuel cycles and providing options to close the fuel cycle, decreasing the amount of waste that must be stored, and simplifying geologic disposal requirements. Perhaps no effort better illustrates how cooperation between national laboratories and industry can enable important breakthroughs in nuclear energy than the long-running collaboration between Argonne and General Electric, Hitachi Nuclear Energy. This collaboration stretches back to the 50s in the days that we were working on experimental boiling water reactors in collaboration with GE, and more recently in GE's advanced reactor design known as PRISM, which also has its root in this public-private partnership. And PRISM was created using principles demonstrated at Argonne's Experimental Breeder Reactor 2, or EBR2, and further refined in the Integral Fast Reactor, or IFR. With the creation of EBR2 and the follow-on design of IFR, the march towards continued U.S. leadership seemed inevitable. However, in the 1970s and 80s, a variety of developments coalesced to move the U.S. away from nuclear energy and next-generation reactors and closing the fuel cycle. Today, the severity of the need to fight rising levels of greenhouse gases in our atmosphere may once again drive the U.S. to regain its place at the forefront of nuclear technology. So our vast nuclear energy infrastructure, developed over decades with the combined capabilities of industry and the federal government, is at a crossroads, where existing nuclear reactors are set to be retired over the coming decades. While light water-cooled SMRs can serve as a bridge to the next generation of advanced reactors, many issues remain that can be addressed by advanced reactor technology. If we wish to chart our way forward towards those solutions, we must once again engage our public and private resources in a new effort to build the next generation of reactors. Much of the technology is developed and demonstrated on a small scale, although substantial work remains. The next logical step is to unify these technical efforts and successfully deploy a test reactor and test bed to demonstrate the advanced reactor systems. The time we have to demonstrate this technology is short due to the age of our current light water reactor fleet. Action over the short term is required to demonstrate new technologies by 2030, when retirement of existing nuclear power plants will accelerate. Thank you, and I look forward to answering any questions that you might have.
Thank you, Dr. Peters. Mr. Batten, you're recognized.
Chairman Smith, Ranking Member Grayson, good morning. My name is Frank Batten, and I'm the president of the Landmark Foundation. We're a private foundation that supports educational, environmental, and human service organizations. I greatly appreciate the opportunity to testify today regarding a positive example of a near-completed Cooperative Research and Development Agreement, or CRADA. And we did this with the Department of Energy's Argonne National Lab. The CRADA relates to what we believe should be an important component of our country's national energy policy, which is the recycling of used nuclear fuel through a demonstrated U.S. technology called pyroprocessing. We have no commercial interest in this area and no financial agenda, but we believe that the U.S. can significantly benefit from recycling used nuclear fuel through pyroprocessing. While private industry can and should play a role, federal government R&D funds are essential if the benefits of this technology are to be realized. Pyroprocessing has been the subject of federal R&D for many years, and Argonne has led the way. The technology is now capable of recycling used fuel from the country's nuclear power plants for reuse to generate electricity in advanced reactors. Pyroprocessing is good energy policy, it's environmentally sound, it promotes effective use of resources, it can contribute to addressing climate change, and it holds the promise of significantly mitigating the country's used nuclear fuel disposition issue. I'd like to briefly summarize the success story of our partnership with Argonne, which relates to the design for a pilot reprocessing facility. I'd also like to brief the subcommittee on an analysis undertaken by Energy Resources International, or ERI. We commissioned and funded the ERI analysis outside of the CRADA. The ERI report analyzes the costs and benefits of using pyroprocessing and advanced reactors on a commercial scale. And I've attached a copy of the ERI report to my testimony and asked that it be included in the hearing record. The Landmark Foundation entered into the CRADA with Argonne over 2 years ago. We invested $5 million, and the federal government invested $1 million in the CRADA. The purpose of the CRADA is to develop the conceptual design and a robust cost estimate for a 100 metric ton per year pilot scale power processing demonstration facility. The CRADA is a particularly good use of the public-private partnership concept. It leverages prior government-funded work, it takes that work to the next level, and it builds a bridge for the U.S. government to move forward with the detailed design for the pilot facility. All of this, we hope, will spur additional federal funding for a pilot facility. The ERI report provides a detailed assessment of the costs and technical factors associated with a realistic fuel cycle using power processing and advanced reactors. ERI concluded that the potential exists to reduce the volume of used commercial fuel requiring permanent disposal by 50% or more, avoiding the need for a second geologic repository. Avoiding a second repository would save the U.S. government tens of billions of dollars. According to ERI, reuse of power processed fuel also would simplify the design of a first geologic repository and reduce the volume of repository space needed by more than 50%. This would significantly contribute to reducing the federal government's financial liability associated with its obligation to receive used fuel from its utility standard contract holders. I'm pleased to be here today to talk both about the success of our partnership with Argonne and the underlying benefits of further developing the power processing technology. Thank you for your time and attention.
Thank you, Mr. Batten. Mr. Gilliland, you're recognized.
Chairman Weber, Ranking Member Grayson, Chairman Smith, thank you very much for the opportunity to testify today about the emergence of new innovative fusion energy concepts and the importance of governmental support and working with U.S. labs. My name is Nathan Gilliland, Chief Executive Officer of General Fusion, one of the leading private fusion energy companies. I'll make 5 key points today and have done so in my written statement in more detail, which I'd like to submit to the record. First, as I would echo what Ranking Member Grayson said, the game-changing nature of fusion energy bears repeating. It's energy production that is safe, clean, and abundant. In a fusion reaction, 1 kilogram of hydrogen is equivalent to 10 million kilograms of coal. It's the energy density comment that you made earlier. Humanity would have abundant energy for millions of years. There's also no long-lived radioactive waste, no chance of meltdown in fusion reactions. The benefits to energy security can hardly be overstated. Second, U.S. support for magnetic fusion programs like ITER and inertial confinement programs like NIF have created an enormously beneficial source of research. ITER and NIF have justifiably been the highlights of the U.S. fusion energy framework and developed key insights into plasma behavior, materials science, simulation codes, and many others. These programs should continue to be supported. Third, because of this historical research, innovation in alternative pathways to fusion have accelerated. These alternative approaches, both in private companies and in labs and universities, offer potentially faster and less expensive concepts. And demonstrable progress is being made, both in these labs, universities, and the private companies. Of particular note, work at Sandia, University of Washington, and Los Alamos are worth noting, as well as the 3 leading private companies, TriAlpha Energy, which is based in Southern California, Helion, which is based in Seattle, and ourselves, General Fusion. The progress of these alternative concepts was featured last summer in Science and Nature magazines. Novel fuels are being tested, new simulation tools developed, and we're all setting records of the stability of our plasma. So real progress is being made. Increased commercial viability, lower cost power, and faster progress are common threads in these alternative fusion concepts. Alternative approaches are reducing costs by applying existing industrial technologies to the challenge of fusion, primarily avoiding costly large lasers or costly superconducting magnets. Some have novel ways to protect the fusion reactor from neutrons. Others have simpler ways to convert heat into electricity. But of course, there are no silver bullets. These alternative approaches tend to be less researched and studied and are simply newer. The physics have not been fully explored. But we would argue the viability and efficacy of these alternative approaches can be demonstrated for less money. Some will show rapid progress and others will not. But dollar for dollar progress or failure can be demonstrated much more quickly. Fourth, though the majority of fusion research has been publicly funded, there is a place, and an important place, for private companies who can build on previous research and potentially innovate faster. The Human Genome Project is a great analog and a great example. The NIH built a core of research that was very strong, and from this, private industry was able to efficiently and rapidly innovate to sequence the genome. We see parallels in fusion energy. World-leading historical research is being done at labs and universities and has led to rapid innovation. And just like every energy industry, oil and gas, solar, wind, there will be multiple approaches that succeed in fusion. It's not a winner-take-all industry. Fifth and finally, going forward, we'd like to see more open innovation and information sharing across private industry, labs, and universities. For example, we all use computer simulation. It's a very important tool for us. We'd like to see co-development of simulation codes, more sharing of simulation codes. Another thing we'd like to see is greater emphasis on exchanges of physicists and PhDs across private industry and government labs. This leads to better sharing of historical research, current research, and the private sector would absolutely put resources into doing this. And labs and universities can help here at no cost to them. Ultimately, more cooperation between government-supported efforts and private industry can only accelerate progress. There is no value in silos. Let's push for more private-public partnerships, as Dr. Peters mentioned, and I'm sure Dr. Varmintola will as well. Let's push for more private-public partnerships to share data, build faster, and accelerate progress. The world needs fusion, and the faster the better. Thank you.
Thank you, Mr. Gilliland. Dr. Varmintola, you're recognized.
Good morning. Thank you, Chairman Weber, Ranking Member Grayson, and other members of the subcommittee for holding this hearing on this important subject. I believe, as many others do, that it is important to the future national security, energy security, and environmental quality of the United States that ample supplies of competitively priced nuclear energy are available. Unfortunately, it appears that nuclear energy is dying in the U.S. There are a few new plants being built. Several have closed recently, and most of the 99 existing plants will be closed down within the next 40 years. To place this in context, last year nuclear was 20% of the electricity consumed by Americans who paid $80 billion for it. We believe this death spiral can be avoided, but it will require active involvement by the U.S. government. The energy market is indicating that existing nuclear power technology is not commercially viable. For nuclear power to play any future role, the U.S. will need new, safer nuclear power technologies that will produce significantly cheaper electricity. However, the private sector will not be able to develop this on its own. The investments required are very large, they are risky, and in any event will take more than a decade before they might yield any revenue from electricity production, and even longer to yield any profit. As these new options are developed and private firms begin to see their way to risk reduction and making profits, private investment will increase, the government will be able to withdraw, and the market will decide which would be commercially viable. Let me now discuss GA's interest in a new advanced test reactor. We have a new reactor concept that needs a testing facility. We call it EM2. And we designed it to address the four most prominent concerns with nuclear power: its safety, its cost, its waste, and its proliferation risk. We believe it is a potential breakthrough technology for the United States. However, research is required to realize it. To develop EM2, a compact gas-cooled fast reactor, we looked at what physics indicates we must do. One, we must go to higher power densities through a compact reactor core using fast neutrons. Two, we must go to higher temperatures, so a higher percentage of the heat produced is turned into electricity. By doing this, we can make the same amount of electricity in a smaller reactor, small enough that it could be made in a factory and shipped by truck to a site for deployment. We believe we could increase the efficiency of power production from percentages today in the low 30s to the lower 50s. The bottom line is we believe that we could reduce the cost of electricity up to 40% below that of existing nuclear reactors and reduce their waste by up to 80%. But to do this, we have to develop new materials that will be able to endure the higher temperatures and endure the more energetic and neutron-rich radiation environment inside the reactor. We need a new testing facility with high performance characteristics in which to do this research work. But there are also a number of other companies and national labs that are advocating the use of fast neutrons and going to high temperatures, albeit with different advanced reactor designs. These also require a new testing facility that conduct tests in, say, 3 years that would show what happens to these materials in an actual advanced reactor during a period of 30 years. It would not make business sense for any company or even all interested companies together to pay for the capital costs to construct such a facility, given the large investment, the risks, and the very long lead times involved for return on investment. Currently, there is no U.S. facility with the requisite high-performance characteristics to do this type of research. The best we have are the Advanced Test Reactor at Idaho National Laboratory and the high-flux isotope reactor at Oak Ridge, but neither of these is appropriate for a number of reasons. The best in the world is in Russia, Bor 60, but this is being shut down soon for other reasons. In any event, it would seem odd to develop such a national security technology in Russia. Therefore, we suggest you consider building such a facility in the United States. It would be called the Versatile Advanced Test Reactor. It would be a highly neutron-rich, fast reactor capable also of producing thermal neutrons. We like versatile because it should be designed in such a way that it could be used to test all new reactor concepts, whether they involve molten salt, a liquid metal reactor, a liquid lead bismuth reactor, a gas reactor, or even light water reactor. The Versatile Advanced Test Reactor would be a user facility in the same way that the DOE Office of Science manages other highly successful facilities. It would contribute to the public good by providing the development of future nuclear energy options. This is an excellent example of what the government should do because industry cannot or will not do it. The U.S. has a great opportunity to lead the world and give nuclear power its best chance to become economically viable. This committee could start by enacting a law calling for a study to be done with industry participation to determine the design for such a reactor, what its capabilities would be, and what it might cost. We believe that if the U.S. were to build such a test facility, it would be key to the development of nuclear reactors that really could spark a true renaissance of nuclear power in the United States. Thank you for inviting me to share our views and for your interest in finding ways to sustain an extremely important future energy source for our nation.
Thank you, Dr. Varmintola. I now recognize myself for 5 minutes to begin the questioning. Mr. Batten, you've come here today with a unique story of a charitable foundation that has invested in a specific process of nuclear fuel recycling, all for the purpose of jump-starting an advanced reactor technology that would reduce waste, increase resource utilization, and mitigate proliferation concerns, obviously. So how do you hope this, I think you pronounced it CRADA? CRADA, right, Cooperative Research and Development Agreement, will make a difference, and what would be the benefits to the United States from successful pyroprocessing and IFR, or integral fast reactor deployment? And then I've got a follow-up question about something you said. How do you hope this will make a difference?
Maybe I'll start with a little bit of background. I live in Norfolk, Virginia, which is only a few feet above sea level, so it tells how we got into this.
How many feet?
A few feet,
okay.
Like 2, 3, 4 feet, depending on where you are. So we're very concerned about the rising seas that could be caused by climate change. And so we looked around for, well, what could we do to help with that transition to a low-carbon energy? And we concluded that lots of people were working on wind and solar and batteries and savings of energy savings, all of which are very important and all of which deserve federal research dollars. We found out that not nearly as much attention was being given to nuclear power. So within that, it seemed like there were two issues. One was nuclear waste. Was there anything that could be done to reduce the nuclear waste problem, since that's such a hindrance to the expansion of nuclear power? And power processing seemed like a very promising technology to be able to reduce the nuclear waste problem. And of course, advanced reactors, fast reactors, when coupled with recycling, also lets you use much more of the energy in uranium. The current, light water reactors use about 1% of the energy in uranium. Fast reactors with recycling could use 99% of the energy in the uranium.
Okay, and I applaud you for that, by the way. Kind of a follow-up question. You said in your comments, if I was heard correctly, that the pyro processing was developed in the United States?
It was developed at Argonne National Lab by their work in Chicago and also by their work out with the experimental breeder reactor 2. They have a fuel cycle facility attached to that.
Okay.
So Argonne really developed that.
But do I understand that France uses more reprocessed fuel, as it were, than we do?
Yes, France, the U.S. currently is not recycling fuel. France is reprocessing using aqueous reprocessing.
So they're not using our technology?
That's correct, yes.
Okay.
The difference is the aqueous reprocessing produces pure plutonium, which people are obviously concerned about as a proliferation risk, whereas the pyro processing produces a mixture of plutonium, all sorts of different isotopes mixed together with other transuranics, or those other elements to the right of uranium.
Would you compare and contrast a cost analysis to the two? Are they roughly the same, or do you know?
I do not know the answer to that.
Okay. Dr. Varmintola, given the United States budget constraints, obviously Congress must be careful with every dollar we spend. That said, as many of you have already said, there are some activities that the private companies cannot undertake, but where the federal government can actually support the research and infrastructure to support that private investment. So, Doctor, can you explain how an open access fast reactor user facility could enable private industry to deploy stranded capital that is simply waiting to be spent on research and development for new reactor designs that are more efficient and even safer than today's technology? That's my question. But before you get there, one of the terms I heard bannered around about this process is if we would support the development of a library where, for example, we could have the resources and companies could come in and kind of draw from those resources. And I think you actually had or maybe it was Dr. Peters who called it a test reactor and a test bed. Was that the term you used?
Yes, sir.
Okay. And so, Dr. Varmintola, can you explain how that open access fast reactor user facility would help?
Yes. First of all, currently there are companies that are spending R&D in trying to advance their advanced reactor designs. In the private sector, the amounts of money that go towards this, at least currently, relatively low. We focus mainly on the high-risk issues that need to be reduced in order to make decisions about going forward. However, a large fraction of the issues that need to be addressed require a new test facility. Now, if such a test facility was built, this would enable the private sector to be able to go to these facilities, utilize more of its capital to be able to do the testing and reduce the risk associated with realizing these advanced concepts. As I said in my testimony, the type of reactor we're looking for is a high-performance reactor. This would speed up testing. The productivity associated with what companies would do would go up, and it would enable us to be able to make decisions, rather significant decisions, about going forth and actually building these advanced reactors.
Okay, thank you. And back to Dr. Peters, you pointed out that the U.S.'s non-proliferation mission could be adversely affected by foregoing the timely development of advanced reactors for export, because that void will be filled otherwise by supplier nations. Would you elaborate? I think most of us understand, but would you elaborate on how exporting reactor technology is a component to the United States security and non-proliferation mission, please, sir?
Sure. Let me start by saying that past shows us that when you look at the worldwide reactors that are operating, U.S. export led to that, and the regulatory process the U.S. established is also gold standard worldwide. So the past tells us that we can actually export our technologies and our ideas and have a positive impact and be a leader. So now the matter of exports outside of a national lab's purview, it's a policy and industry play, but past shows that it can work in the future. So I would say, it definitely should be looked at very carefully, and I think it does establish leadership. But I do want to make the point also that there's a component of this that also is related to the R&D and the necessary infrastructure, because if you the national labs and university system in the U.S. is world class in the nuclear space, but we have it now, but if we don't continue investing, we'll lose that capability. And that's an important part of getting that seat at the table, very important part of getting that seat at the table. Having that world-leading S&T capability is also very important. So from the labs and universities' perspective, that continued investment, but getting on the path of research, development, demonstration, and ultimately deployment domestically can't do anything but help international leadership.
Along those lines, you said in your prepared testimony that you provided the NRC will need to establish a new licensing structure to accommodate the next generation of more safer, efficient, safe reactors. So can you explain to us further why the NRC will need to establish a new licensing framework?
So it's within they have a broader framework, but they have a set of general design criteria and detailed regulations that are focused on light water reactors, pressurized water reactors, and boiling water reactors. So if we're going to move forward with licensing advanced reactors, we have to go and develop general design criteria and all the necessary licensing basis to license those machines. Now, there is an effort already funded by DOE working with NRC, and the labs are supporting that, but it needs to be scaled up, let's say, in terms of budget, and also accelerated if we're going to actually license these machines.
Gotcha. Thank you. And I apologize to my colleagues. I'm a little over time. The gentleman from Florida, Mr. Grayson, you're recognized for questions.
Thank you, Mr. Chairman. Mr. Gilliland, some of the problems associated with using fission for power generation are meltdowns, radioactive waste, and nuclear proliferation. There are other problems as well. Can you please elaborate in your testimony on why fusion may be able to avoid some of the problems associated with fission?
Yes, absolutely. Ultimately, it starts with the reaction itself. So fission is a large atom that can react spontaneously. Fusion is done with hydrogen only, and it's impossible for fusion to happen spontaneously. So it's a difficult reaction to get started, therefore very difficult or impossible for it to start on its own. So in a fusion reaction, there are the byproducts are helium and heat, or high energy neutrons. So there are not long-lived radioactive waste materials produced at all. Using hydrogen, certainly difficult to figure out how that could lead to proliferation challenges as well. So we do have normal safety challenges that any power plant would have. It's not that it's without risk completely, but certainly long-lived radioactive waste is not one of them.
All right. Now, your company is developing and advancing a unique fusion energy design that falls into a category of fusion energy concepts called magnetized target fusion. What is that?
Magnetized target fusion, I think it's worth stepping back for a second and describing kind of the mainstream long-standing fusion programs at a high level. ITER and magnetic fusion use a low-density plasma, much less dense than air, and hold it together with large superconducting magnets, and hold it together for long periods of time, even continuously. Laser fusion is sort of the other extreme, where a little fuel pellet is slammed with lasers in nanoseconds or picoseconds. The idea behind magnetized target fusion and other what we call middle ground fusion approaches is that those extremes are extremes. They're extremes makes them expensive. So big superconducting magnets cooled to 2 degrees Kelvin are expensive, as are using the world's largest lasers. It's not that those pathways aren't viable; they're just they appear to be expensive. So the middle ground uses density between the two and speeds of compression, speeds of shrinking that plasma that are much slower than laser fusion. So in our case, we compress a plasma called a spheromac plasma in about 80 microseconds, which is obviously much slower than the picoseconds or nanoseconds of laser fusion. So the idea is just simply put, it's to avoid the extremes and become much lower cost and ultimately more practical.
Now, my understanding is that your design has no permanent home in U.S. energy research, but is funded by a temporary ARPA-E program that you noted yourself in your testimony. Is there a value, in your opinion, to having such research permanently funded as a regular part of energy research by the federal government?
Sure. So I would comment, ARPA-E has done a great job on a fusion program. I think they're still in the middle of negotiating with the various recipients. So, whether or not we are a recipient of that, I don't know at this time. However, to your question, I think it's vital that the U.S. support this middle ground, and I think the primary reason is that a lot of significant progress can be made for small dollars. So some of these middle approaches are absolutely viable, some are not. We don't know which is which yet, but it will not take billions of dollars to determine that. I think funding is one, but I think in my testimony I mentioned, let's work together, labs and private companies around simulation codes. Let's work together around exchange of PhDs and physicists. I think there's some simple things we can do to accelerate progress as well. But ultimately, I do obviously support this middle ground of fusion.
What's a rough time frame that you could provide, allowing for no undue optimism, for achieving net energy production?
It's a difficult question. There's no question about that. I think there's an interesting graph that plots Moore's law against fusion progress. So fusion progress being how much energy out of a reaction are we getting in, or how much are we getting out for what we're putting in? And it's actually quite interesting. They parallel each other. So I think the question is, we're nearly there. I think the large programs have determined that it can be done, and now it's a question of just how do we do it commercially, how do we do it economically? And I think that's the question, right? So I think there's two steps involved. One is building an alpha power plant or a prototype plant that demonstrates reliability, and then second, building commercial plants. So I'm spinning around your answer or your question a little bit, but we're certainly several years away. I would like to think that we as a set of alternative concepts can get there in the next 5 or 10 years, given the basket of options that are out there. I'm optimistic that within that basket, in that time frame, we'll get there.
Thank you.
The gentleman from California is recognized.
Thank you very much, Mr. Chairman. Years ago, I used to believe that the environmentalist community was being alarmist when it came to nuclear energy. And I have seen a lot of alarmism come out of the environmental community that has not been accurate. But let me just say that in the case of nuclear energy, as time has gone on and more information has been available, I think the environmental community over the years has been on target on this issue. The fact is that nuclear energy, as we are now using it, is very dangerous. And as it is now, there is leftover waste to deal with the way we produce nuclear energy today. So that's a big concession for me. In the number of debates that I have with environmental activists, they were right about that. But we are capable of technologically meeting those challenges that were brought up. And whether it's leftover waste or whether it's a safer way of producing nuclear energy that wouldn't have the same type of dangers associated with our current plants, we can do that. I especially want to acknowledge our friends at General Atomics, who have been in the forefront and spending a lot of their own money over the years trying to develop a new and next generation of nuclear energy that is safe and won't have the massive leftover waste problem for decades, if not centuries, to come. But the government has to play a role in this as well. If we're going to have the benefits of nuclear energy, and because private companies can't make this jump on their own, but once that jump is made, our private companies will be able to then, on their own, to build these next generation of nuclear power plants. So I would like to go on the record absolutely saying this idea of having an open access facility is perhaps the most important thing we can do to provide America's long-term energy interests, because it doesn't mean that just General Atomics or any other company that is investing in this and looking down this road. It will be available to all of those approaches, and after this facility is available, we will know which is the best one to go with, which is the best way to go. So this is what is not a good use of our money, however, is something that is aimed at fusion rather than fission. And we can do these fission reactors with all due respect to the last witness. Oh boy, now we know it's possible. We've spent, I don't know how many billions of dollars to find that it's possible. No, after spending billions of dollars, we should actually be in a point where we can, not only is it possible, but we'll have it ready within 2 or 3 years, whatever that is. But we're nowhere near that with fusion. But we do know that if we focus on this next generation of fission reactors, especially modular fission reactors, we actually can do it and do the job rather than just know that it's possible. Let me note that we have spent, I'd like to ask my friend from General Atomics, the actual configuration of the next generation of nuclear reactor that you're working on. The people in Japan were sold a bill of goods that what they were given was totally safe. And now what happens, we've seen this catastrophe in Japan. Would the model you're working on, and perhaps the other models that people are working on, would that protect us from that type of situation that they have in Japan?
Yes, thank you for the question. And actually, I brought some results of our work with me. This is revolutionary new cladding. It's made from ceramic materials. These materials undergo a transition from solid to gas at about 2,600 degrees. They lose their strength at about 2,000 degrees centigrade. I point out to people that the metal that exists in current light water reactors begins to lose strength at about 700. So this increases the safety margin by a factor of almost 3. Okay? Also, these materials even benefit a light water reactor, and we've developed them for our advanced reactor. So there's another version of this that we're working on to make light water reactors meltdown proof, because this material does not react with water at any temperature. So you can't have the kind of runaway reactions that generate huge amounts of heat inside the reactor that melt the core. It's not possible with these materials. So if we invest in materials like this, it has multiple benefits across a number of reactor designs. Of course, the one that we're most interested in is EM2, and EM2 has a certain unique characteristic to it in that it utilizes these materials, but what it does is it provides a high-power, small reactor. So you get more bang for your buck in terms of the capital investment and the output of the reactor, and at the same time one that is inherently safe because of these materials that we're developing. But these materials require significant amounts of testing to prove them out, so this way we can convince the Nuclear Regulatory Commission that these type of materials can actually make fission reactors safe. And that's the principal reason why we're pursuing this.
If you indulge me one more question, Mr. Chairman, would that be possible to retrofit some of our current so some of our current light water reactors, which have a lot longer life on them, could be refitted with that material?
Exactly. So I have two types of cladding. This cladding here, the thin one, goes into light water reactors. The rods, these rods are 14 feet tall. They go into the reactor and they have fuel inside. This one is for EM2, which is a totally different design. We packed more fuel in the core of EM2 to increase its power density. But this material ensures safety.
Thank you very much, and thank you, Mr. Chairman, for holding this hearing. I think it's vitally important that we not write off nuclear energy as a potential source for energy. It's, as the witnesses have stated, it's clean. It will not, I don't believe in global warming, but I do believe in clean air, and this will go a long way to providing energy for the world and for the people of the United States. Thank you very much.
I thank the gentleman who yields back, and now, Mr. Lemensky, you're recognized.
Thank you, Mr. Chairman. Thank you for holding this hearing, and I'd like to say I do agree with Mr. Rohrabacher, except for I do believe in global climate change, but I think together we need to work to bring nuclear energy. It's something that we have to, first of all, maintain America's leadership on the innovation when it comes to nuclear energy and nuclear technologies, and we need to transition to advanced nuclear technologies like fast reactors. And I hope to get language in the Competes bill supporting advanced nuclear reactor test facilities. So I think it's very important that we do move ahead, and research is critical, and that's what we're here to talk about. For Dr. Peters, Illinois has been a leader in nuclear reactors since the first reactor was developed by Enrico Fermi at METLab, now renamed Argonne. Thank you for your leadership in keeping Argonne and Illinois a leader in nuclear energy innovation. And moving forward, I want to ask, what are Argonne's research and development priorities, and how do these priorities complement work at other national labs and fit into the DOE strategic direction?
Morning, Congressman. Thank you for the question. Argonne continues to have strong capabilities, broadly speaking, in advanced reactor design and analysis, fast reactors in particular, but also a broader set of expertise that also supports light water reactor sustainability, and also thinking extensively about potential future fuel cycle options, either repositories or closing the fuel cycle. So we have that broad set of capabilities where we also are working very closely with our sister laboratories, in particular Oak Ridge National Lab and Idaho National Laboratory. So we're spending a lot of time as 3 labs working with DOE, in cooperation with DOE, to ensure that the labs are working together strategically and complementing each other. And so I think that's a very healthy conversation, and it's ongoing, and it's been very positive. But our strategic interests, we really think it's important. Our primary role would be to really think about what's the next set of systems that one would develop, demonstrate, and ultimately commercialize, both in the fuel cycle as well as reactors for electricity. And then also using our foundation in nuclear to also be a part of the technical basis for securing safe and secure operation worldwide as nuclear expands.
Thank you. And I also want to move on to other collaborations, specifically between the national labs and industry, because I think that's important to improve U.S. research investments by leveraging private sector expertise and helping to bring new technology to the market. I know Argonne has been particularly effective in engaging with the private sector, for example, collaborating with the General Electric on the development of experimental boiling water reactors. These reactors now make up about 1/3 of the U.S. reactor fleet. So I wanted to ask you, Dr. Peters, what can we do here in Washington to support these types of collaborations?
The lab, thank you for the question. And the history of the lab has been that we've been deeply committed to these partnerships, and that's an important part of it. But currently, the Department of Energy is making it very clear that they value the labs working in cooperation with industry. So that's really, really important. So I know the work of this committee on thinking about how we continue to enhance tech transfer, I'll call it, from the labs to industry. Those conversations are very healthy and very important. Again, DOE is deeply committed, but I think we can always continue to talk about it and continue to explore ways to become more efficient. But from the lab's perspective, we do basic science, we do applied science and technology, but ultimately, regardless of time frame that it takes, the research has to ultimately have an impact, and that means getting out to industry, into the market, and improving people's lives. So that's at the highest levels of commitment that the labs have, and I think the DOE shares that. They do share that commitment, and I know you do as well. So continuing to just look at the detailed processes and continue to figure out how to become more efficient, and align the values of industry with the federal R&D infrastructure are just vital.
Thank you. I'll yield back.
I thank the gentleman. Mr. Holtzman, you're recognized for 5 minutes.
Thank you, Mr. Chairman. Thank you to all of our witnesses. Dr. Peters, it's always so good to see you. Certainly love being able to tell the great story of all the good things that are happening in Illinois. Good news for the rest of the committee is having you here means they don't have to listen to me, and they can be much better informed hearing from you. So
Amen.
I'm glad you're here. Hey, watch it. Illinois is certainly the leading nuclear state in the nation, and I do appreciate the traditional role the federal government has had in development of nuclear technologies. Earlier this year, the committee passed legislation that I had introduced, among other things, that would require DOE to examine their capabilities to authorize, host, and oversee privately funded reactor prototypes and related demonstration facilities. It was certainly good to hear from our witnesses today about the ongoing debate that this department, the research community, and the industrial base has already been having on this topic. I wanted to address my first question to Dr. Varmintola and also to Dr. Peters. Some argue that open access user facilities are a more effective mechanism to enable investment and accelerate technological growth compared to a cost-shared agreement between the government and the private sector to deploy new technologies. I wonder which type of federally funded investment do you believe is most effective to accelerate this growth, and wonder if you could explain it.
Yes, thank you very much for the question. So I can only tell you the way industry looks at cost-sharing arrangements. Industry is very conservative. It has to do with the nature of what we do. We produce products and we have to show a bottom line and a profit. So dollars we spend are very precious. What happens in my experience with cost share is that industry will look at it and take an opportunity to go with something low risk and take advantage of the fact that the government is willing to provide a cost share for it. And what this does is it reduces innovation, in my opinion, because what we need in industry is more risk-taking. Of course, the national labs undertake risk-taking, but if we're going to try to advance technology and get it into the commercial world, industry has to also undertake risk-taking. So, in my opinion, over 40 years of being involved in the research and development in this nation, what matters the most in terms of high-quality R&D is competition and being able to challenge the community. And by the community, I just don't mean universities, I mean national labs and industry, to undertake high-risk, high-payoff research. The way to do that is to adopt standards, very high standards, and also goals, technical goals that challenge the community and allow industry to compete. And I think without a cost share, you're likely to drive industry towards more risk-taking than less risk-taking. And it's really up to the agencies to do this. They have to take charge of this and actually meet the standards that are required.
Thank you. Dr. Peters, before you answer, let me add one part to this that I'd like to get your comments on, and then I'll leave the rest of my time to you. How would you envision our national labs, such as Argonne, assisting in the process with NRC? Does the DOE need to take a more informative role with NRC? So I wonder if you could talk a little bit about, again, my first question there, but also following up a little bit on what the chairman had started.
Good morning, Congressman.
Good morning, Dr. Peters. Good to see you.
So on the first question, in my testimony, I referred to a test bed, and actually, I think it's very similar to what you're referring to in the legislation. And Dr. Varmintola used the user facility model as a way to have the conversation, and I agree with him. You can set up a set of facilities that provide the ability to test and demonstrate advanced technologies, and do it in such a way that you can either do it in a pre-competitive, more open sense, or you could actually have aspects of it where industry is actually bringing resources and doing proprietary work as well. We do that, as you know, at the existing scientific user facilities like the Advanced Photon Source. There's a model for that. So to me, I think there's a lot I agree with Dr. Varmintola, that translates. So there's a lot to be done to define what this test bed would look like. And that would have to be something the labs, the government, universities, and industry work together to define the requirement set. But I think they would be able to push us ahead in a way that you're not necessarily picking a winning concept, but there's a test bed there for all to come, test their concepts, demonstrate their concepts, and ultimately that will then lead to what makes sense in the market.
Great.
On your second question, so specifically, I'd addressed the chairman's question earlier on the NRC. Specifically, there's activity already going on between the DOE and NRC that the labs are supporting, our lab and a few other labs are supporting, to develop what we call general design criteria. So looking at advanced systems like a high-temperature gas reactor, a sodium fast reactor, for example, and developing detailed general design criteria that one would use that would inform the regulatory basis going forward. So we know what needs to be done. It's more a question of what's the priority, because right now the NRC is understandably completely focused on regulating the existing fleet and also watching the new construction of some of the Gen 3 Plus reactors in the southeast. But we know what we need to do. It's just a question of if we want to get to these advanced machines in a more timely manner, we just have to increase the priority on the effort.
Yeah, I agree. And I do believe Argonne and other labs have a pivotal role, a vital role, and want to make sure that we can have you be part of that. So thank you, Chairman. I appreciate the time. Yield back.
Thank you. In that context, very quickly, if I may, according to research, the Manhattan Project, which was 42 to 46, cost $2 billion. Okay, 90% of that was in the production of the factories and the fissile material, and less than 10% was actually used in the R&D for the weapons. In today's dollars, that's $26 billion with a B dollars. So who's going to invest that kind of money? Thank you for the indulgence. And the gentleman from California is recognized.
Thank you, Chair. I represent Lawrence Livermore National Laboratory and Sandia National Laboratory in Livermore, California, in the 15th District, and appreciate our witnesses here and also Dr. Peters, the work you do at Argonne. Is that correct? And my question is for Mr. Gilliland. And in your testimony, you're pretty forceful on the potential power of fusion energy. And, for example, you write that the game-changing nature of fusion energy bears repeating. Energy production that is safe, clean, and abundant that would change the landscape of energy forever and greatly enhance energy security. At the two national laboratories that I represent, they do a lot of work in fusion energy. For example, at Lawrence Livermore, they have the National Ignition Facility, the largest inertial fusion facility in the world, which is an amazing research tool, which has produced a wealth of information. But its primary goal right now is to assist in the maintenance of the nuclear weapons stockpile. However, we have long-term hopes that it can be a sustainable energy source in the future. So keeping that in mind, and Representative Lofgren, who's on this committee as well, she has worked with me on supporting fusion. But keeping that in mind, do you think, Mr. Gilliland, that the federal government is spending enough to support fusion energy research? And if not, do you have a dollar amount in mind as to how much more we should spend? And would it be helpful to have an actually dedicated funding source for research into all different types of fusion, including inertial, for energy applications?
I would echo your comments on the National Ignition Facility and their leadership in the fusion energy space. You mentioned that their primary goal is around weapons. However, they're making huge steps in fusion energy as well. I think the number is they've improved by about 100 times their fusion yield in the last 3 years. So I certainly believe that continued support and even enhanced support of National Ignition Facility is warranted. Similarly, Sandia has an alternative approach called Z-pinch, which I won't get into the details of, but they've also demonstrated a huge amount of progress. So we're certainly supportive of all of the concepts of fusion, including magnetic fusion that General Atomics is quite involved in. I think where funding could and make a big difference is in some of the alternative approaches. Most of the dollars go toward magnetic fusion or inertial confinement fusion, both of which have benefits and both of which have created really a base of research that everyone is benefiting from. I think the difference is that some of these middle ground concepts like ours and a number of others do have the potential to be faster and less expensive because of we don't need lasers or superconducting magnets. So I think it's a basket of alternatives and it should be approached that way. Each have their pros and cons across the spectrum. So I can't give you a dollar amount, but certainly support and enhanced support, I think, is absolutely warranted because the final point I'd make is, whether it's fission or fusion or others, I mean, the world needs more energy, and energy is fundamental to the entire economy. So it's not one or the other; it's all.
Thank you. And also, with respect to Dr. Varmintola and Mr. Peters suggested that the federal government should develop a new nuclear reactor facility to test innovative reactor ideas. Now, knowing that we have few federal dollars allocated for this type of research, and it doesn't look like the trend is going up; it's actually going down. Do you have if you had to prioritize between fusion and nuclear reactors, any thoughts on that?
How to prioritize between fission and fusion? Is that your question? I think they both have their pros and cons, right? I think fission certainly has the waste issue to deal with, proliferation and so forth, but there's certainly a number of viable pathways that fission has demonstrated with small modular reactors and so forth. So I think that it's a little bit of an apple and orange comparison. I think a demonstration facility could have both. I don't know why it couldn't have both. I think creating that regulatory framework is helpful for all of us, and again, I think it would be beneficial for us all to have it at one location.
Thank you, and Mr. Chair, I yield back.
I thank the gentleman from Illinois, Mr. Foster, is recognized.
Thank you, Mr. Chairman, and I appreciate the opportunity to attend this despite not actually being formally on this subcommittee. Let's see, first question, I'd like to say that I'm a big fan of turning up research in this field. The payoff, if one of these comes up with a home run and a really viable zero-carbon energy source for our world, is enormous. But ultimately, the thing that I struggle with is the business of design studies that look at projected cost of electricity, which is ultimately the end point on this. And so the difficulty you get into there is you're comparing technologies with different levels of maturity. And ultimately we're resource constrained. We've now decided to make what looks like between a $3 and $4 billion bet on tokamak fusion, leveraging that to roughly 10 times that amount offshore. And we may or may not decide to do the same sort of leveraging and making a U.S. investment into offshore fission technologies that are being developed. And so, but ultimately what we're looking for is the cheapest way of making zero carbon electricity. And so there is certainly a role in doing design studies, just say pretend the technology works and what would the cost of electricity be if it all works according to your dreams. There are big dangers there because you can lose that bet or find that to make it work you have to add a lot of cost to things. But how do we, how should Congress think about and handle that? Is this best left to committees? The problem is that committees, knowledgeable people on committees are always composed of advocates for their technology, and you can balance the committee in different ways and get whatever answer you want, depending on how you choose to balance those committees. And so I guess my question is, do you think that we're putting enough effort into the sort of design studies that I'm talking about, where you say just pretend the technology works, does it ever have a chance of being cheaper? This is something that's often talked about, for example, in terms of laser-driven fusion, that if you just look at the wall power efficiency, everything you'll have to do to get the compression. I guess, sorry I missed your presentation, Mr. Gilliland, but from what I understand, your technology, you anticipate a higher efficiency wall plug efficiency in terms of getting the fusion to happen. And that's that's a real argument when you look at the final thing. But my question is, are we putting enough effort into that and the right kind of effort into these studies of what the theoretical cost of electricity should be? Or are things just so far away and such a big spectrum in their R&D readiness to be able to make those sensible comparisons? So anyone wants to comment on? Yeah, Dr. Varmintola.
I can only talk about how General Atomics has tried to address the issue that you are raising. We've looked at basic physics to tell us what we need to do in order to be able to improve the price point of electricity. Of course, it's tied to financial models, but when you look at the financial models tell you a story. So, for example, the biggest driver for cost is the cost of capital, which has to do with the risk premium associated with what you're doing. And so we thought about that, and what we need to do there is change the paradigm as to how we fabricate, manufacture, assemble, and deploy nuclear reactors. Okay. The next most important, which is physics-based, is efficiency. And we carefully looked at this, and we tried to look at how we could increase the efficiency of a nuclear reactor. And we've come up with a design that indicates that we could get over 50% efficiency, which is 20 percentage points above what we can do today. And I'll remind people that for every percentage improvement in efficiency, that adds $500 million to the bottom line over 30 years. So you're talking about $10 billion more in the pocket of a utility who's selling electricity. Okay.
You're also talking about turning up the peak operating temperature.
Correct.
Components and
right, and that's the reason why. It's the reason why you have to go to new materials, because the materials can't deal with it. But this is fundamental research that we have to do, and of course the government should be sponsoring that type of high-risk research, because the payoff can be tremendous. And so the next one is capital cost, right? And of course, what you want to do is try to reduce the capital cost. The thought is, well, if you make reactors smaller, you can reduce the material cost, but you have to have enough power output to compensate, right, for the reduction in size. So that, again, drives you to a higher temperature, higher power density, and so on. The physics tells you what to do, and that translates into the financial model. Then, of course, it's a matter of achieving the technical goals through research that you need to achieve in order to be able to get there. And that's really what a facility that we're advocating, this new type of test facility, user facility, would do. And that user facility would create competition, natural competition amongst those who are trying to achieve these advanced reactors. And to me, that's the best way of sorting out which ones are going to survive and which ones are not.
All right, well, thank you.
I'd make an observation. Is that okay, Mr. Chairman?
Yes, sir.
Good morning, Congressman. So I would say you're aware of the various analysis tools that are done by the various parties that are out there, as you said already in your remarks. And you have the DOE EIA does projections, and then, of course, all the various advocacy groups do their own projections, as you pointed out. And now you have a QER and a QTR that the department's doing that I think are important steps. But my observation would be that I think you're on the right track, because I think we haven't yet gotten to where we have an objective set of tools that can think about advanced technology and technology insertion into the discussion. At least I'm not aware of very many robust objective tools there. So to me, if we're going to sit here and talk about important things like fusion and Generation 4 fission reactors, they're at various stages in their TRL level, right? And so and I think we could probably model that. We could understand that and model it, but we're not really doing it in a comprehensive way, looking at the whole energy system. So I think there would be a place for that kind of analysis. I'm not aware of a robust objective program that's going after it, though.
Yeah, well, it would have to span, the whole fusion and fission space, and that's difficult to assemble.
Right. Yeah, and it would be complex labs, universities. It would be quite a big undertaking, but very informative, I think.
Thank you, and I guess I'm well over time, and I should yield back.
We'll just take it out of your next 5 minutes. But the gentleman yields back, no problem. Mr. Batten, I said earlier that I applaud you, your collaboration, your efforts and stuff, and thank you again for being here. But I wanted to give you, and I went way over my time, Mr. Foster, by the way. What I
remember.
What I wanted to ask was, would you elaborate on your experience with working with Argonne National Lab in the present company, and what was the best thing about it, the worst thing about it, the most frustrating thing about it? How could you improve? I know I'm putting you on the spot. How could we help improve the process?
Well, this was the first CRADA we had ever participated in, so it took us a while to just get ourselves up to speed on the process and understand the agreement and that sort of thing. But after we did that, we had a very good experience working with the lab in terms of just kind of working out the cooperative agreement. I would say by far the best thing about our experience is the technical work of the lab. I mean, I'm a layperson scientifically, but my impression is the Argonne's technical work has just been superb. And of course it built on, that's because they have great people, but also they have all this expertise that they've built upon all their past work.
Okay, Dr. Peters' check is in the mail to you.
That's true.
And
from my point of view.
We love hearing that. Any suggestions to improve? I know you were kind of on virgin territory there.
Right.
Any suggestions on how we can facilitate improving that process?
I do not have any. No.
Yeah. So have you produced an outline, a white paper on how the next collaborative process will work?
Well, I guess the question, I'll maybe answer that a little bit more broadly, sort of what would the next steps be. What the CRADA produced, the main thing the CRADA produced was a conceptual design which produced a cost estimate. And the CRADA report should be out in a couple months and we'll know what that cost will be. Because what we hope is that Congress will authorize the development of the pilot facility, but we thought you wouldn't really want to do that until you had some idea of what it would cost.
Well, and that's why, I referred to it earlier as a kind of a library facility where, we could provide the facility and then books and the stuff could be there for people to come and check out, if you will. And that would hopefully be an incentive for us to be able to take that next step you're talking about. And Chair now recognizes Mr. Grayson.
Thank you. Uranium is fuel for nuclear reactors. If the industry were healthy, one would expect the price of uranium to be going up. In fact, the price of uranium is now 1/4 what it was 8 years ago. What does that tell us about the market's assessment of the future of nuclear energy? Dr. Peters.
I'm not an economist, but I would say that the current state of nuclear energy vis-a-vis the role of natural gas in that, the role of deregulation, et cetera, is having significant impact on the economics of nuclear reactors as they currently operate and also as currently envisioned to be built in the next, say, decade. But I would say, uranium is abundant. There's plenty of it. We don't need to mine it because we can still use uranium that's been mined decades ago. As part of various non-proliferation programs, we can get uranium. So part of it is that there's hundreds of years of uranium. So one of the interesting questions would be why recycle? It's hard to make an argument to recycle just based on uranium reserves because there's plenty of it. So you're asking a very complex question, but I would say the economics in 2050 that would drive what the energy system looks like are going to be very different than they are today.
Dr. Varmintola, is the market basically trying to tell us that nuclear fission as a market is doomed, given the fact that uranium now costs 75% less than it did even 7 years ago?
Just so you understand, the General Atomics is in the uranium mining business. We have uranium mines in the United States as well as overseas.
Not doing too well lately, are you?
So, my boss is a very astute businessman. So he's in that business for a reason. And while, of course, with Fukushima, we saw a decline in the use of uranium in Japan. Germany has got out of the nuclear reactor business. Switzerland has sort of followed suit. The demand for uranium obviously has gone down, but I can tell you that there have been new deposits found, abundant ones, in Australia. With China surfacing as a major nuclear energy producer, they have the largest number of reactors in development now, 30. That'll be a lucrative business. India as well. And I have to say, with fast reactors, it's not just uranium that is a fuel. Thorium is also. And if you do an analysis of using both uranium and thorium as a source with fast reactors that have a closed cycle, you have enough based upon known reserves, including the waste, to last you 2,000 years. That's just known reserves. If I went into the ocean, there's more uranium in the ocean than there is on land. And
water also. There's more water in the ocean than there is on land.
Yeah, right. But there's a huge amount of uranium in the oceans. So the supply of uranium and even thorium is extremely large. And I think it's great that a fuel is cheap and that you can derive so much benefit out of it. It's great. Right now, I can say to you, tritium costs $100 million a kilogram. Right now, tritium, the known amount of tritium in the world, is $100 million a kilogram. So one of the challenges in fusion is to figure out a cost-effective economic way of producing it so this way it could self-sustain itself. Oh.
All right. I'd like to ask Dr. Peters. Dr. Peters, you used some interesting language in your testimony. You said that the country's leadership in global nuclear energy could be further compromised, that our country runs the risk of defaulting on the return of 7 decades of investment in nuclear science. By the way, you can't actually default on a return in investment. That's not possible.
Will the gentleman yield?
Sure.
Now, this is spoken by a guy that has informed us that there's more water in the ocean on land. So y'all might just take that with a grain of salt. I yield back.
Chairman needs to listen more closely to my quips. That's not correct. And we should be careful not to forfeit the legacy of many brilliant minds. Another questionable mixed metaphor. But here's the thing. All you're describing here is the idea that we would take a step back from our nuclear fission program. And Germany has taken 2 or 3 or 4 steps back from its nuclear fission program. It's planning to shut it down entirely. What does Germany know that you don't know?
Germany buys nuclear electricity from France, would be one point that I would make.
Mm-hmm.
While Germany's made certain, I'm not going to go any further than that. So from my perspective, setting aside that maybe I mixed metaphors, thanks for the feedback, appreciate that. I would say that we've invested as a country in unbelievable nuclear S&T capabilities. And if we do not move forward with the next generation of technologies, that's going to erode. It's eroding slowly. And if we don't invest in the labs and the universities and the next generation, we're going to be sitting here a couple decades from now with no capability and absolutely no seat at the table.
But another interesting mixed metaphor. But Dr. Varmintola, Germany has paid the price for its deciding to eliminate its nuclear program. The price is that they are now the leader in solar technology around the world. They have the healthiest solar energy market of any major country in the entire world. Is that a price that we should be willing to pay as well?
In my opinion, no one has a crystal ball in terms of what to expect in the future in regard to the abundance or lack thereof of resources. That we didn't expect natural gas to be so cheap. And by the way, the U.S. government invested 30 years ago, 40 years ago, in the fundamental technology that enabled fracking to produce this. So from an energy security point of view, your best bet is to have as many energy options as possible. Of course, we can't predict the future. And nuclear is a technology that can meet the requirements that people are asking for in terms of the economics, the waste reduction, the proliferation risk, and the safety. There's nothing in the laws of physics that would prevent that. What has happened, unfortunately, to nuclear, it's been on the same technology for 60 years. If you look at any major technology that the U.S. has developed and continues to develop, it's all been driven by research and achieving performance, higher performance levels. Nuclear has not changed in 60 years. Its efficiency is back where it was, and we're using submarine technology that was designed, obviously, for submarines. Any other major technology that I can think of has been driven by research and development and performance. Pick transportation, either ground or air. Pick communications. Look at the mobile devices we carry around with us. Look at computer technology. Computer technology has undergone 5 paradigm shifts in the last 100 years, all based upon an advancement in a fundamental technology to advance computing. So nuclear stood still. And I think what Dr. Peters is talking about is the need for a research and a research-driven community. The nuclear community is not research-driven, in my opinion, and I've been around research for 40 years. It's not. They want to build things. That isn't the way to develop new technology. You have to do research that drives. It's discovery first. Discovery drives invention, and invention drives innovation. That's the process. Right now, nuclear has remained stagnant because research is lacking. We haven't gone to higher performance technologies and materials to drive its performance. That's what's going to matter in the end.
Thanks. I yield back, and thank you all for your testimony today.
I want to thank the witnesses for coming in today and for your testimony. It's been very, very informative, and we appreciate y'all being here with that. Our hearing's adjourned.